Case study, Revamping Cybersecurity Defenses in Financial Institutions, a machine learning approach at SecureBank. Cybersecurity has become one of the most pressing issues in our increasingly digital world. At the heart of effective cybersecurity measures lies the power of machine learning. Machine learning provides the foundation for developing algorithms that allow computers to analyze data, identify patterns, and make decisions with minimal human intervention. This capability is crucial for detecting and mitigating threats swiftly and efficiently. Imagine a large financial institution, SecureBank, which handles millions of transactions daily. The bank's cybersecurity team is headed by Dr. Emily Waters, an expert in machine learning and data science. SecureBank has recently faced a series of sophisticated cyber attacks that breached its defenses. Dr. Waters is tasked with revamping the bank's cybersecurity measures using machine learning principles. The first step involves understanding the types of machine learning algorithms available. Dr. Waters explains to her team the difference between supervised and unsupervised learning. Supervised learning requires labeled datasets where each data point has a known output. For instance, by using a dataset of network traffic labeled as either benign or malicious, the team can train a supervised learning model to predict the nature of real-time network traffic. An immediate question arises: how can supervised learning models be effectively trained to differentiate between benign and malicious network traffic? To answer this, the team collects a comprehensive dataset of historical network traffic, meticulously labeled by cybersecurity experts. They employ various algorithms such as decision trees, support vector machines, and neural networks to train their model. The goal is to achieve high predictive accuracy, ensuring the model can generalize well to new, unseen data. A challenge they face is the model's ability to generalize without overfitting. How can the team ensure their model does not overfit the training data? Dr. Waters introduces the concept of the bias-variance trade-off. Bias is the error due to overly simplistic models, while variance is the error from models too sensitive to training data noise. Striking the right balance is crucial. They decide to implement regularization techniques to address this trade-off. Lasso regression, which adds a penalty based on the absolute value of coefficients, helps in creating simpler, more interpretable models and reduces overfitting. Ridge regression, penalizing the square of coefficients, is used to stabilize the model further. Examining the impact of these techniques, the team deploys cross-validation methods like k-fold cross-validation to reliably estimate the model's performance. What are the advantages of using k-fold cross-validation in this scenario? While supervised learning is effective, it may not always be practical to label vast amounts of data. Therefore, Dr. Waters also considers unsupervised learning methods. These models do not require labeled data and are designed to uncover hidden patterns within the data. Anomaly detection is a prime application in cybersecurity, aiming to identify deviations from normal behavior. For instance, an unsupervised learning model might detect unusual login times or unfamiliar IP addresses accessing the system. This leads to another key question. How can unsupervised learning models be fine-tuned to accurately detect anomalies without generating too many false positives? The team uses clustering algorithms like k-means and hierarchical clustering to group similar data points, identifying anomalies as data points that do not fit into any cluster. Principal component analysis is employed for feature extraction, reducing the data's dimensionality while preserving essential variances. Fine-tuning involves iterating on the number of clusters and analyzing the clusters manually to set thresholds that minimize false positives. Adversarial attacks pose a significant threat to machine learning models. These attacks involve subtly altering inputs to deceive the model. Dr. Waters emphasizes the importance of robustness in their models and introduces adversarial training. By incorporating adversarial examples, deliberately crafted inputs designed to fool the model into the training set, the team enhances the model's resilience. The team asks, what strategies can be implemented to ensure the robustness of machine learning models against adversarial attacks? In addition to adversarial training, the team explores ensemble methods that combine predictions from multiple models. thereby enhancing overall robustness. They also employ techniques like defensive distillation, which reduces the model's sensitivity to small perturbations by training it at different temperatures. A critical aspect of their model development involves selecting relevant features. Dr. Waters explains that feature selection and extraction are paramount to the model's efficiency and interpretability. By identifying the most predictive features, the model can run faster and more accurately. They use techniques like recursive feature elimination and mutual information to select the most informative features. What considerations should be made when selecting features for a cybersecurity-focused machine learning model? The team ensures that selected features are closely tied to the domain of cybersecurity, such as IP addresses, login times, and access patterns. They also perform feature extraction using PCA to transform features into a lower dimensional space, retaining the most critical information. Evaluation of the model is another critical step. Dr. Waters insists on using multiple metrics such as accuracy, precision, recall, and the F1 score to gauge the model's performance. While accuracy provides an overall measure, precision and recall offer insights into the model's effectiveness in identifying true positives and minimizing false positives. Cross-validation is employed to ensure the model's robustness across different data subsets. How can the team ensure comprehensive evaluation of their machine learning model? The team uses a stratified k-fold cross-validation approach to maintain the same distribution of classes across folds. They also implement a confusion matrix to visualize the model's performance, identifying areas of improvement. Interpretability is vital in cybersecurity applications, where understanding the model's decisions can be as crucial as the decisions themselves. Dr. Waters introduces techniques like SHAP and LIME to provide insights into the model's predictions. How can these interpretability techniques be integrated into the model to enhance its transparency? The team integrates SHAP values to explain the impact of each feature on the model's predictions, enabling them to identify which features are driving decisions. LIME is used to create local surrogate models that approximate the behavior of the complex model within a small region, offering clear explanations for individual predictions. By implementing these machine learning principles, SecureBank successfully revamps its cybersecurity defenses. Their models, trained and fine-tuned using both supervised and unsupervised learning techniques, demonstrate high predictive accuracy and robustness against adversarial attacks. The careful selection and extraction of features, combined with rigorous model evaluation and interpretability techniques, ensure that the models are not only effective but also transparent. Through this case study, the importance of understanding and applying fundamental machine learning principles in cybersecurity becomes evident. By addressing questions related to model training, evaluation, robustness, and interpretability, Dr. Waters and her team illustrate how machine learning can be leveraged to build adaptive and resilient cybersecurity systems.